Hey, hey, how y'all doing today? Okay, I was just in a Zoom meeting where someone was talking to me and I could hear them. So I'm just going to assume you can hear me. And Brandon verified. Cool. And I'm assuming I can hear you if you unmute, but no one's done that. So I don't know for sure. Excellent. Cool. I appreciate it, Paulo. Okay, so where we stand is just a tiny bit of additional material and last day of content. And so it's a matter of getting ready for and doing the final exam. So I'm just going to do the normal thing and start with sort of administrative related issues. And if you have questions, you'll of course let me know as we go. Trying to let you know where to show up for the final exam. So, like 24 hours from now, I will have already passed out the final exam in room one, I guess building 180, Baker building, room 113. So that's sort of where you enter on the ground floor on the very west, and then you make a quick left turn and you'll see it. It'll be where I am. And I don't know what most of you look like, but most of you know what I look like. And so you'll spot me. It'll be easy. If you want to come by before the exam hits, I've got office hours from 2:30 to 3:50. So yeah, I have another exam for the other class, the Stat 313 group that ends at 2. I want to take a break so I can do a couple things like maybe, eat or something like that. And I'll be back in gear by 2:30. And then you can come by, ask questions, and then with about 15 minutes to go before I'll start passing out exams, I'll say, well, let's take another quick break. And so there's that. Yay. Second thing I want to mention is if you click your way into stuff for this week, you're going to spot that it's like Monday, Tuesday, and Wednesday, just 3 days worth of content. From 2 years ago, the final exam that they had, please just ignore any comments about grades or any comments about the format of their exam because your exam will be different. Basically, think 50% longer than either of your midterms, but think twice as much time to do the test as either of your midterms. And so if you felt rushed for time, you will feel less rushed for time on this exam. But some of you will be using the full 2 hours, and that's absolutely okay. One other thing I want to mention is please bring a note sheet, anything you want to write on it. And because there's always a great question, okay, can I bring a calculator that will do all the fancy things? Like I've got a calculator with an F distribution in it. Sure, go for it. Just when you write down your answer, say, yeah, calculator. So I know where you got your value. Um, Now, I know earlier in class or office hours, someone came in with a really good question that I'm now forgetting what it was. And so, if you remember that, hey, I'm that person who had the really good question, please feel free to unmute and let me remind me of what it is because I wanted to make sure to tell all of y'all. Well, okay, so that person is perhaps neglecting to say, yeah, I'm the one with the wise question. But I'm drawing a total blank on what the question was now. So if one of you unmutes, that's great. Otherwise, I'm going to move forward. Be sure to watch that overnight. Oh, I think I know what the question was. And here's the question. Hey, could we just like turn in our homework later than tonight by midnight? And the reason for that question was like, if you give me extra time to do it, I'll do a better job on it. And my attitude was, yeah, I don't care. But what I would love to be able to do is to post the answers to the homework questions. So that way they come on live after midnight. Not that I'm saying I expect you to stay up till midnight to check the answers out, but if you wake up early in the morning, it'd be great for you to have the answers there lying around for you to investigate, for you to see. Hey, oh, here's the answer. Cool. So, if you'd rather turn things in late, like a day later, uh, or if you'd have a definite opinion about, I'd rather turn in the stuff by midnight the day I was planning on turning it in, and then have the answers available to me, just let me know right now, audibly, or in email within the next 2 hours, and I'll make a call on that one.
Could you repeat that? Sorry.
Yeah, yeah. So, Anthony, if you have an opinion, or any of you have an opinion on the question of should I postpone the due date for the homework from chapters 9 and 10 to be like tomorrow class time? The benefit of that is you get extra time to work on those homework problems. The downside, however, is I won't be able to provide the answers to those homework questions. My intent was to provide the answer to those homework questions like tonight at midnight or just after the due date. So if y'all have an opinion about turn in the homework early, not early, turn in the homework on time and get the answers right away, or prefer to have the homework turned in later, just let me know what that opinion is.
Would we be able to do something where it's like if we do end up getting it done tonight, we could just email you to see what the solutions are? So it's like if people still need extra time, they could turn it in and like still have that time.
I love your idea, except for I'm unprepared to build sort of some auto reply thing with the answers built into it. So, like the idea, how about we split the difference? 9 a.m. Turn it in by 9 a.m. and the answers will be revealed at 9 tomorrow. Cool?
Cool.
Anyone feel free to raise your hand or do a thumbs up if you have an opinion on that one. Or if you have a strong opinion, let me know. But let me know by about 7 p.m. California time, and I'll go with something that seems reasonable to me. But yeah, 9 a.m. to turn in the last assignment, and then also 9 a.m. for the answers to be made available. Seems split the difference, kind of. Okay, cool. So I'm going to call it that unless one of you talks me into something else, and you're welcome to try. Um, oh, yeah, there's one last thing we need to talk about, and that literally is, hey, what about regression? We did something with it before, but we never tested any hypotheses in the context of regression. Could we test a hypothesis in the context of regression? And the answer is yes, we can. So how about we do that? So come on, here we go. So let's think it through. And I'm going to work off of ANOVA because we dealt with ANOVA most recently. And imagine a situation where, okay, come on, do the pick a color. Imagine a situation where you're dealing with maybe a mixing rate for an alloy. Okay, you're mixing two things. I don't know, gold and tin. I don't even know if you can make an alloy out of gold and tin, but let's pretend that Steve knows what he's talking about in materials. And you have different mixing rates. Okay, and so the percent, yeah, gold in your alloy is going to be something that's a number, and it could be either 10%, 15%, 20%, or I'm going to jump all the way up to 30%. So those are the different levels at which we could run an analysis of variance. Literally, what I could do is collect data at the 10%. Okay, I could collect data at the 15%, at the 20, and at the 25% context. Okay. And I could tackle the question with ANOVA. My null hypothesis is that mu for 10% equals mu for 15 equals mu for 25 or 20, I'm sorry, 20 equals mu for 30. And you're saying, okay, we could reject that perhaps. My gut feeling is that you would reject that. I mean, seriously, look at the data that I've suggested for you. the 30% gold group is quite different than the 10% gold group, my gut feeling is the ANOVA would say, yeah, there is a noticeable difference between the means. But some of you said, oh, hold on. You said to yourself, not out loud because I couldn't hear you. You said to yourself, maybe there's a linear trend. And if you're looking at, I don't know, some conductivity, I mean, I don't even have a clue whether the conductivity would change. But if you're thinking that the conductivity might change across the different levels of gold in this alloy, why not fit a trend line? The trend line and the ANOVA would be effectively trying to tackle the exact same problem. Is there a relationship between X and Y? Now, maybe that would the way I'd express it in regression terms. Remember how we talked about there's an intercept and a slope? I'm going to say that the slope, which I will call beta 1, here's my model, that y is beta 0 plus beta 1 times x plus errors around the trend line. The beta 0 plus beta 1 times x tells me a typical value of y. That little epsilon error means you go up or down a little bit by, just randomness of luck. Okay. Beta 1 might be 0. And those sort of are going to correspond. If the slope really were 0 in the context of a linear relationship, that tells me all 1, 2, 3, 4, 5 means, all four means at 10, 15, 20, and 30 would all be the same on average. So there may be no relationship, beta 1 is 0, or perhaps all the means are the same. Or there is a relationship, in which case I'd say the slope, beta 1, is non-zero, or perhaps that the means aren't different from, are different from each other, in which case you reject the null hypothesis. So we have a belief that there is a situation where we could randomly sample from a population or do an experiment. If you have X's and Y's, the question is, are the Y's going to depend on the X? Is there a correlation between the Y's and the X's? Am I able to predict a Y from X? These are the real issues. Okay. Any questions about that setup or that introduction context?
Can you explain why B1 equals 0 is equivalent to the first null hypothesis?
Okay, so let's draw it a little bit differently. Great question. Let's suppose the slope was 0. That says there is a constant XY relationship. Whatever the percent gold is in the alloy, then the average value of Y is going to be, read it right off the trend line, and the trend line would have the average Y, mu, at the same level for each of those four contexts. So I think I answered your question, but I'm not sure. Would you like to rephrase?
No, that makes sense. Thank you.
Yeah. The key is there is either no relationship, no hypothesis, or alternative, there is a relationship. And in the context of the truth being a linear trend, shoot, we could talk about nonlinear trends in another class, another term. In office hours, we have ways of adopting these various methods we're teaching you in 312 to sort of match other contexts. I'm just saying if there is a trend, and I assume for the moment that it's a linear trend, a slope of 0 says there is no trend, that the mean is always the same. It doesn't matter what the X value is at all. So let me show you an example of a situation where maybe that would be reasonable. So I think I may have mentioned these data earlier this term. And if not, I'm going to mention it right now. We've got data in one county in Illinois on the yield in terms of bushels per acres planted for corn in each of the years, 1890 to 1927. So, this will be data that could be used in a crops history class, perhaps. If I looked at Graph Builder, you could say, does Y, the yield, seem to depend on X, the year? Okay, come on, X, the year. It looks, does Y, the yield, depend on X, the year? And it seems as though the trend line is a little bit slopey. The question is it statistically significantly non-zero. In terms of the slope, is this slope such that, is it steep enough such that we reject the belief that there is no trend in favor of the alternative hypothesis that there is a trend, that the slope is non-zero in value? So I'm going to leave this hanging over here, and let's formalize it a little bit. In general, in regression, if you're attempting to test a slope, we're going to have to believe a model. And the model we're going to believe, it's sort of like Hooke's law. Remember Hooke's law? The length that a spring stretches to is going to be, well, shoot, there's the original length of the spring plus then a stretchiness coefficient times then the weight that you add to the spring. And let's just say, real life is not always perfect, that there's some error variability. That epsilon is just error around the trend line, if you will. There is a true relationship between x and y. If you tell me x and beta 0 and beta 1, the beta 0, the length of the spring originally, and beta 1, the slope, that for each extra gram of weight, it stretches an extra 0.2 centimeters. I guess I could say 2 millimeters. But 0.2 centimeters is what I'm going to go with. Yeah, if you tell me beta 0, beta 1, and you tell me x, the weight that you put on it, I'll tell you the typical weight that the spring will stretch to. Check. Got it. If this is the truth, and a couple things about the epsilons. One is that the epsilons are one independent of each other. So in other words, if I tell you the spring stretched out a certain amount and oh, this epsilon was a positive 0.3, doesn't impact, okay, any other epsilons for any of the other weights that we could attach to the spring. The epsilons don't depend on each other. Two, that they're normal in shape. And three, that the variance of the epsilons is constant. Okay, so the variance of epsilon is just some number sigma squared. And note that I'm saying regardless of x, implicitly that there is a constant variance. Okay, normal constant variance. And this is another way of saying linearity. The expected value of those epsilons is exactly 0, again, for any x. So this is the context of this linear model. Essentially, what I'm telling you is, in terms of corn yield and rainfall data, if you tell me the year, and let's go with 1900 because I can spot 1900 easily there. Kind of draw it vertically. In 1900, there is a true average value for y, and I'm going to draw in the true trend line here. I'm going to go with not blue, I'm going to go with green. So here's the green population truth. This is indeed beta 0 plus beta 1 times x, okay? And x being year. And in 1900, there is a distribution of the possible epsilons around the average. Here is the average x shown here for that given year, 1900, and there's a distribution of possible y's that we could observe. Okay, but if we went up to 1915, right around there, that is the average value for y, and there is a distribution of possible y's centered at the 1915 average. Okay, so I apologize. Let's get rid of that one too. And there we go. Now it looks better, closer to what I wanted. In any given year, there is a distribution, and the distribution shifts northwards towards higher yields as each year goes by. Year is the value for x, and if I tell you the year and you knew the intercept and slope, you could tell me, aha, the average value of the yield, but then there's variability, which we model with that little distribution there. In this context here, I might have a hypothesis. My null hypothesis, H0, could correspond to beta 1 is 0. Indeed, there is no change in the average yield across time. On the other hand, beta 1 is not equal to 0. These are the two default values that Minitab JMP, any stat package out there is going to be using for your null hypothesis. Literally, no relationship is the null hypothesis that invariably is the default option for JMP or any stat package. The alternative will correspond to there is a relationship in some fashion. Null, no relationship. Alternative, there is. So let's show you how you could do this analysis. If actually, if you have any questions first, I'd love to answer those questions before I clear the screen and then go on to the analysis.
When you say the multiple epsilons, do you mean like is there like one for every data point, one for every
Yes.
possible x value, or
Yeah. Let me make that really explicit. I'm going to say yi is beta 0 plus beta 1 times xi plus epsilon I. Yeah.
and the epsilon is just how far away that data point is from what we would expect with the our current equation?
Yeah, if there is a general trend in corn yield to be going upwards across the years, yes. If that's true, in any one year, the growing conditions are going to vary a little bit. The soil will vary a little bit from, the winter snow melt and then how much it rains and when it rains and that sort of information. So epsilon might be a really crappy year and you get like a very negative epsilon, like over here in 1901, the yield was really low. So John, I think I answered your question. Would you want to
Right.
rephrase?
I guess kind of to keep going with that, how do
Yeah.
we know that every epsilon has the same, like follows a normal distribution and keeps the same uh standard deviation?
I love the question. Let me do two things. One is say, if this were a semester class and we were meeting not during summer, but across 15 weeks, there would be two class sessions on this, and we would show you exactly that. But if you are intrigued enough to move forward, we're just going to let you know that stat 3520, which is offered fall term, will go into the answer of that question. Or 3530 actually as well, but 3520 is typically taken first. Crappy answer, I'm
Gotcha.
sorry, John, but or we could talk in office hours if you'd like to, but it's beyond the scope of this term.
If I didn't have a final tomorrow, I would take you up on that, but I'm just focusing on what I need to know right now.
Yeah, no, but your question's a good one because how do we really know we could use the method we're talking about using? And the answer is we could check to make sure that these assumptions or requirements are valid. And you ask the question, how can we check that? And the answer is, we'll tell you another time. So I'm gonna not have office hours tomorrow, well, other than in class, but you won't be focused on that. I'm saying if you wait until late August, I'm happy to chat in office hours next term about this, or you could just take another freaking class. Yay, take more school. Okay. By the way, since age 5, I've never left public education, so clearly I've got a problem. Addicted to school. So here's how we're going to pull this off. Year is X, the yield is Y. If we tried like before modeling fit Y by X, it's going to say, well, what might be dependent? Well, the yield may depend on the year. Does yield depend on year? And I'm presuming in a linear way. And notice that just over here it says, oh, your X is quantitative, your Y is quantitative. I'm going to fit a trend line. Okay. We get the plot without the trend line even shown in. But if I say add that trend line, you might have noticed earlier this term that it gives you, interestingly enough, a p-value down here at the bottom. Let me show you information about the items in this last row of the parameter estimates. Things that you maybe wondered about last time, but you didn't directly ask. Okay. So our test statistic for the null hypothesis, let's go with the null hypothesis. The null hypothesis is that beta 1 is 0. The alternative hypothesis is that beta 1 is not equal to 0. My test statistic is called T. It is our sample slope beta 1 hat compared to the 0 that hypothetically beta 1 should be if the null really were true. And we're going to divide that through by a number we'll call the standard error for beta 1 hat. Okay. The standard error, that's a familiar thing. Okay, we had y x bar 1 and minus x bar 2 and divide through by the standard error. So the standard error tells me the typical amount of this numerator. How far does it differ from the true population slope? How far away is my sample slope from my true population slope? That's the standard error. And an equation for that standard error, SE for beta 1 hat, is equal to, and I'm going to sort of use some terms that I think are okay. N minus 1. Okay, so you see n plays a role there. S sub x and S sub e. S sub e is, think it through as the standard deviation of the residuals. So how far is the typical data point away from the trend line? I'm going to try and draw in what a couple of those residuals are in yellow over here on the graph. I'm trying to add a couple of yellow lines. These are how far away are the data points from the trend line. That is going to be standard deviation of the residuals, or S sub E. Let's also circle over here, root mean square error. In this case, it's 4.09. In other words, if I'm trying to predict the yield from the regression line, this root mean square error, or S sub E, says I'm going to be off by about 4 bushels per acre. Sometimes I could be off by more, but usually we'll be within 2 root mean square errors, 2 values of S sub E, up or down from our prediction. So how far off could we be? S sub E, check. And this suggests something. If the value of the residual standard deviation, if that S sub E is small, that says we've got the data tightly clustered around a trend line. Smaller numerator causes the precision level to be greater, a smaller standard error, if you will. Thus, a larger value for T, more clarity in that test statistic T. What else? Okay, n. If n in the denominator, yeah, if n goes up, if we had more data, yeah, like, not that we could really do this, but what if we had not just this one county, but the adjacent county in every single one of these 38 years? You'd think n is now double. Well, my gut feeling is, even with the same amount of variability around the trend line, the fact that there's twice as much data tells you I have more confidence in my slope estimate, or alternately, in terms of a test statistic, what we have is a larger value for T because the standard error, the denominator term, is now smaller. S sub x, that is equal to our friend, the standard deviation of the x's. Let me give you another equation for this value for T, and I'm going to give it to you approximately. That's equal to n times the root of 1 minus r squared over n. Shoot, that was not even a good drawing of an n minus 2. Okay, so that is a goofy algebraic identity. I'm not trying to justify it, but what I am trying to tell you is, hold on. Hold on. I want to check something. Is that the way I want to phrase it? Actually, let's completely erase most of that and I'll fix it. You ever know something and then you know when it looks really wrong? It's r squared over 1 minus r squared. And I think Actually, let me just bail out of that one entirely. I'm going to say it is in our textbook. And what I was trying to say is emphasize if you have more data, the value for the test statistic T will go up. And the larger the value of R is, indeed, the test statistic T will go up. But I'm not remembering the exact equation right now. Damn it. I should remember these things. Oh well. So yeah, the test statistic T is what is calculated for you down here at the bottom. What we can see is we've got our sample slope. Okay, sample slope 0.149. The standard error, that's our standard error. It's the denominator of that test statistic T. Literally, if you take the 0.149 and divide through by that standard error, it gets you your T ratio, in this case, 2.5. And you use the regular t-table to get your two-tailed p-value to reach a conclusion. So we could do a hypothesis test about our sample slope. Same thing as before. I guess you do need to know one other thing, and that is degrees of freedom is n minus 2. Okay, so that's a hypothesis test. Typically, I use data and let the data, and let the software just tell me what the answer is. But if I give you numbers like, okay, the standard error and then the slope, you're home free. If you have that information, you're good to go. Okay, any questions about that or something related to that?
So once we have the t statistic and the degrees of freedom, we just use the t-table like normal.
That was a good joke. Like normal. No, you use the t-table. Yeah. Yes, exactly. And the final is written such that, yeah, you've got a t-table for you. And so the questions are written assuming you have a t-table. But I didn't think chi-square would be all that helpful. And so, yeah, t-table, use it. Okay, so that's one question. Is there a relationship between X and Y? And if we reject the null hypothesis of no relationship, you're telling me that there is a relationship. You're telling me beta is a non-zero. Beta 1 is non-zero. How about a confidence interval, a 100 times 1 minus alpha percent confidence interval for the actual slope beta 1? Okay, it's going to be beta 1 hat, your estimate, plus or minus, I'm going to say T critical value, T alpha over 2 in the upper tail area, and degrees of freedom is just n minus 2. And then that's going to be multiplied by the standard error for beta 1 hat. So it looks like before. You've got your estimate of the number you're trying to estimate. There's your estimate. Plus or minus, well, how confident you want to be? 95% confident. Well, use about a 2. Times then the standard error, a measure of how far off we could reasonably be. The software will automate all that for you. And this is the sort of thing that you could do by hand. But if you're thinking, yeah, I don't want to do it by hand, and you're working away inside GMP, I learned something recently that's sort of cool that I was surprised to find. If you literally mouse down inside the parameter estimates, under columns, you could say, yeah, just give me my lower confidence interval and mouse down again. And under columns, give me my upper confidence interval as well. I would say I'm 95% sure that for each additional year that goes by, the slope, which tells me the increase in yield, should be 0.026 to 0.272. So in other words, I'm going to be waiting about 40 years for an extra bushel per acre on average, but it might be as low as 4 years. So somewhere in the range 4 to 40 years, we'll have an extra bushel for every acre. Okay, the estimate is 0.149. That's 0.15. If I wait about mathing here, 6.5 years, okay, I should be in the extra bushel per acre range. But instead of saying where it's just 6.5 years, I could say it's going to be in the range 4 to 40. 95% sure of that. So the confidence interval for the slope, we get it, and we can put a margin of error on it. Any questions on that guy? Okay, so there's one last thing that is sort of key, and that is a 100 times 1 minus alpha percent confidence interval for, I'm going to say beta 0 plus beta 1 x nu. Okay, so I'm going to call that mu nu. Literally beta 0 plus beta 1 x nu. And the lowercase nu looks sort of like a V, a scrolly V. Yeah, really what we're saying is if you tell me X, even if you don't know beta 0 and beta 1, but have estimates for beta 0 and beta 1, you could say, well, there is an average yield for a fixed year. You tell me the year, say 1930. Plug in 1930 to your equation. Okay. My confidence interval is then beta 0 hat plus beta 1 hat times that new x plus or minus t alpha over 2. It's always t, it's always 2 times then a standard error of sorts, and that standard error has a fun equation. It's going to be 1 over n plus x nu minus x bar squared over the standard deviation of the x's. Actually, let's pull the parenthesis down. Okay, so how many standard deviations above the average x is your new x? X new is a particular value for which you want to know the average y. You could plug in that average value into your trend line and plus or minus twice something. And what we're seeing here is it depends on how far that x is away from the typical x. Now I'm going to ask you to think it through carefully. If you got this seesaw like you all used as kids on the playground, if you have one kid really far out at the one end, do they exert a lot of leverage on the seesaw? The answer is yes. It's a physics word, leverage. The further away you are, the further away you are from average, okay, the more a slight error in the slope will impact the actual value of y on average. Okay, so we can see that it's just a matter of take your x, okay, compare it to x bar, divide through by standard deviation, put it in standard units, square that, and then add a 1 over n. And then we're good. There we're good. Take a root. We're good to go. So let me show you how I could pull that off. Inside JMP, the whole thing is handled for you. I guess what I could do is I could say, aha, I've got the line fit here, and under the linear fit, I could show you a confidence level for the average. Okay, so mean confidence limit formula. And over here, you might have spotted when we turned on the mean confidence limit formula, it gave me these two new columns. Again, if we go down under here under mean confidence limit formula, it creates these two new columns that say, well, in any given year, like what year? 1917. In 1917, the average yield we're 95% sure would be in the range 31.5 to 34.9. In 1927, again, you get a range of plausible values for the average y. Not individual y's, but the average y. And so that's sort of a nice little feature. We can also graphically show that if confid shaded fit. It shows me a value, a plausible, it's a range, a plausible range of values where the trend line would actually appear. So sort of flat is almost plausible. Steeper than we estimated is almost plausible. Give or take a little bit, yeah. Then this range of values, this bow tie shape tells us where the actual x's should be on average. And it's going to correspond largely to how far away from average are you? Okay. Let me do one thing because I think I made, again, one small mistake and I want to check my math here. And damn it, I don't have it in that sheet right there. Okay. Okay. Well, I'm gonna say I believe that there may be a small error and um okay, yeah, there is a small error. Let me rewrite that equation for you. And this is working from memory, and I'm pretty good on that one, but not today it seems. So again, a 100 times 1 minus alpha percent confidence interval for mu nu, which is beta 0 plus beta 1 times x nu. Again, you tell me the x, okay? And I'm going to say, well, times beta. Well, I don't know beta. And then add beta 0. I don't know that. So there is an average value for yield out there. That would be beta 0 plus beta 1, both hatted, okay, from the regression output, x nu, plug it in, plus or minus t alpha over 2, times then the root of, and here is where you're thinking 1 over n plus 1 over n minus 1, and this is where I apologize. I should have had the n minus 1 times x nu minus x bar over the standard deviation of the x's squared. I knew I was forgetting something. What drew my attention to that lack of a 1 over n there in that second spot is, what if we had more data across the exact same years? There should be more precision. And indeed there is. Okay, so here is the equation we could use, but the software will give that to you for free. We're happy with that. Okay. Any questions about a confidence interval for the average value for y for a fixed and given x?
What is the degrees of freedom there?
N minus 2. Yeah,
Uh,
great question.
how do we know when it's n minus 1 and when it's n minus 2? Weren't there some cases where it's n minus 1?
Okay, great question. In a regression context, the degrees of freedom is n minus 1 I sorry, shoot, I just lied. N minus 2 because we have to estimate an intercept and a slope. And in a looking at one mean context, it's n minus 1. In the compare two means context, the pooled is n1 minus 1 plus n2 minus 1. So there's a lot of different contexts. My recommendation, John, is to just write down degrees of freedom equation for the particular method because it will vary enough. There is a general rule for degrees of freedom, which makes a bit more sense the class that follows this one. So I feel the first class in a stat class, it always is frustrating because like we tell students, oh, and here's another thing that will make more sense in the next class. So n minus 2 degrees of freedom for regression. But you can see I've got an n in the denominator and an n minus 1 in the denominator. And earlier there was another equation with an n minus 2 in it. It's just you got to remember them or learn the general rule. So does that help at all? Not much.
Yeah, what was it for two means again? Just writing it down.
For two means, yeah, literally the method our book suggests is just use the software. And if you're willing to go with a pooled t-test that Steve doesn't recommend, it would be n1 plus n2 minus 2 degrees of freedom. But I don't like the pooled t-test, and I don't want to use that method.
Okay.
Yeah, we get a little picky about a couple things. Um, yeah, the general rule in the next class really does clean up a lot of the sort of frustration that students could have with this thing called degrees of freedom. The an approximate version of the general rule is how many values do you have, in this case, like n data points, and how many parameters do you need to estimate Well, beta 0 and beta 1 both need to be estimated. So it'd be n minus 2. In the two mean context, it's like, oh, n1 data points over here and 2 data points over there. Subtract 1 from each of those. But that approximate rule falls flat, and we do fix it later in that next course. Okay, another question maybe. So I'm going to close with a comment, and that is, oh my God, there's a lot of stuff. Okay. And I don't want to sort of dwell on things too much. You might not have noticed, but you might have noticed from talking to friends who've taken Stat 312 in the past. We've gone through a lot of stuff very quickly, and it's because of the 2 days per week approach to this class. If we had this class as like a 2 hour class, yeah, and then 2 days off, and then a 2 hour class, and then a weekend, and then repeat the process for 10 weeks, everything would be a little bit cleaner and easier. And there would have been actually an extra little bit of time to tackle certain additional problems. I pulled a few topics out that normally would be covered more thoroughly. And I try to de-emphasize a few things to focus on what is the key, what are the most important things for you guys from the engineering point of view. So I got office hours, finish them up today, but we will do those tomorrow before the exam. And I want you to go ahead and not worry about anything, but focus on studying and moving forward and getting ready for tomorrow's test. Enjoy. We'll talk to you soon. I'm going to stop the share.
Thank you.
Yeah, we'll see you soon.
Uh,
Yeah.
Without watching through all of the videos, is there anywhere where you could recommend if, like, this might just not exist, but is there somewhere where we can find like a comprehensive list of like topics that we've covered, just so I don't forget one that we went over?
Yeah, I would recommend just going through every section, yeah, of our book, which had homework problems assigned, and just write down those as the topics. And you could then go down the list and say, check, 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 got it. Or hold on, I'm not sure I remember that. And then you do a quick read.
Gotcha. I'm just writing that down.
Yeah, if there were homework problems assigned from a section, that's a section where we would like you to have some understanding. And then if you look and go through the reading and you say, he didn't really emphasize that in class. If you were right that I didn't emphasize something in class, it's probably of lower importance.
Gotcha.
Yeah.